Euler's formula says that the exponential of the imaginary root I times a real angle theta is cosine theta plus I sine theta. This formula makes it convenient to solve linear systems of differential equations, for example, as one would do when describing how voltages and currents fluctuate over time in an electrical circuit connected to household alternating current, or when comparing how shocks and struts handle slow rolling motion versus sharp jolts during a car ride. In this slide deck, we demonstrate Euler's formula, we illustrate how to plot complex exponentials in the complex plane, and we point out Euler's identity. Recall that e to the x can be expressed as a power series, 1 plus x taken to ascending powers and divided by ascending factorials. What happens if we substitute for x the quantity I theta, where I is the imaginary root and theta is a real number? To find out, we substitute I theta into each location where we see x written in the power series. The first and second terms are copied directly. Notice that squaring the root I gives back -1 by definition, whereas the cube of I spits out not only the -1 corresponding to 2 powers of I, but also another I giving negative I. The fourth power of I is the square of -1, which is +1. The pattern continues in subsequent terms with i's and 1's and pluses and minuses alternating in the same way. Rearrange the terms. Group the real terms, meaning those with even powers of theta, to the left, and group the imaginary terms, those with odd powers of theta, to the right. Factor out the common I attached to the terms with odd powers of theta. The terms with even powers of theta form the power series for cosine theta, and the terms with odd powers of theta form the power series for sine theta. Euler's formula says that e to the I theta equals cosine theta plus I sine theta. Unlike the exponential of a real number, the exponential of an imaginary number has both real and imaginary parts. E to the I theta is called a complex exponential. We can plot the real part of the complex exponential using the real number line from -1 to 1. The real part of the complex exponential is the stuff that is not attached to the imaginary root I. We can plot the imaginary part of the complex exponential using a line of imaginary numbers from -I to I. The imaginary part of the complex exponential is the part of e to the I theta attached to the I. Together, these axes define the so-called complex plane. For example, at some generic number theta, the real part cosine theta might be this horizontal length, while the imaginary part sine theta might be this vertical height. The blue circle marks the location corresponding to e to the I theta in the complex plane. Sketching a right triangle and a unit circle, we interpret the number theta as an angle of rotation relative to the real positive axis. The angle theta is the length of this blue arc. As theta increases, the complex exponential e to the I theta walks around the circle. Consider the angle theta equals pi. Here, the real part of the complex exponential is cosine pi, and the imaginary part is sine pi. The cosine of pi is -1. The sine of pi is 0. Thus, e to the I pi equals -1. Euler's identity beautifully relates 4 basic fundamental mathematical structures: Euler's number, the imaginary root I, pi, and unity. We demonstrated Euler's formula, e to the I theta equals cosine theta plus I sine theta. We illustrated complex exponentials in the complex plane, and we pointed out Euler's identity, e to the I pi equals -1.